Hey there, geometries. This is Mr. Rising once again, and this lecture is all about triangle proportionality. And the big idea is after we know two triangles or whatever figures really are similar, then we can start using these properties to figure out what unknown measures are, such as distances, heights of mountains. This is really the foundation of trigonometry. When we say, hey, we've got similar triangles, then I can figure out relationships on one triangle and apply it to something else. And the vocabulary word that we're really talking about here is indirect measurement. And the idea is you can use formulas, proportions, measurements, whatever, on one object. And you know that using those tools, you can figure out what the dimensions are on another object. And the classic example of this is, if we're going to try to go to Mars, we better figure out how our biosphere, our habitat, is going to work before we get there, because we can't figure out the parts. We can't take the measurements after the fact and build it. So what we do in engineering is we design everything here. We can scale it up. I'm going to pause and take this call. Don't worry, they didn't call me in to be Supreme Leader of the United States. I said, look, I've got to take care of geometry first. Anyway, going back to the engineering example, we can scale it up. We can figure it out without actually having to go there. The same thing works in the ocean. Places where it's very hard to take measurements, we can map the Earth and then figure out how big or small things are. So it works out great. So that's what we're doing in this lesson. If you're following along in geometry textbook, the Holt-McDougall variety, this is lesson 7.4. And it starts out with the triangle proportionality theorem. And the idea here is, if we have two triangles that are similar, then we know that their side lengths are proportional. And what happens here too is, even when you have parallel lines cutting through them, then we can set up a proportional relationship. Check this out. So I know triangle DAE is similar to triangle BAC. Boom. So I know this entire length AB would go with AD. But what happens here is when you cut it with parallel lines, then you can say, well, wait a minute. That means this part, 10 and 15, can form a proportion with 12 and this side. So this actually ends up being a shortcut, because now I'm not comparing 10 with 25. I'm comparing 10 and 15 to 12 and this unknown length. And that's what you're looking at here on this side. I love this little icon I was trying to make. Kind of looks like a sleeping square smiley face. But anyway, so what we're saying is set up a proportion. 10 over 15. Oh, you know what? Let me just delete it. Bam. Gone. 10 over 15 goes with 12 over x. I'm going to call this x, EC. I don't know what it is. Again, proportions. In this case, because the variable's in the denominator, I cross multiply. X goes with 10, 10x. 15 goes with 12, that's 180. Divide both sides by 10, and I get x is equal to 18. And that also then would mean this entire side is 30. Just a little example. Pause if you need to get this in your notes. The converse of triangle proportionality is also true. In this example, it doesn't say that these triangles are similar. However, since if I set up their pieces as a proportion, for example, 25 over 30. Now again, that's not the entire length of dt, it's only this portion of it. But wait a minute, if this might mean that this is a parallel line, and therefore I would have a triangle proportionality set up. So let's test it. 25 over 30 goes with 20 over 24, and if I simplify both of those fractions, I get 5, 6 equals 5, 6. Therefore, I know right off the bat that these triangles are similar and that these two lines here are parallel. Extending that one step further is when you have multiple transversals. Now, remember, a transversal cuts across two or more lines. So this line segment right here, AE, is a transversal of these three parallel lines, and BF is another transversal of these three lines. Well, the point here is, again, I'm taking a slice of something. I know that this segment here, AE, if it continued with BF, would actually form triangles. And so, wait a minute, if that relationship from the previous example holds, where I'm saying this piece over this piece goes with this piece over this piece. Well, the same is true here. I can say, wait a minute, AC over CE better work like BD and DF. And you can see why this really impacts us on our world. When we do maps, we often use parallel lines. And you think about globes and other maps where we have lines of latitude that are parallel, right? And we can use that information to figure out all kinds of measurements all over the Earth. And when we do a little more trig, you'll see how this all plays out. You're going to get examples like this, where you have a bunch of parallel lines and it says, well, how long is Kn? Well, let's figure out where Kn is first. Kn means, oh, from here to here. All right, well, I've got a bunch of parallel lines. I have some known lengths up top. Let's just set it up as a proportion. All right, I know 2.6 on the lower segment, and I'm looking for Kn, the total length of the lower segment. Well, let's set that up as a proportion with what we know from the top. 2.6 goes with 2.4, good, AB. And then Kn is the entire length. Well, what's the entire length from A to D? Well, if you add up 2.4, 1.4, and 2.2, you do get 6. Lo and behold, when you solve for Kn, you get 6.5. So now I know this entire length here is 6.5. You don't actually have to solve each individual segment unless it asks for it. Work smarter, not harder. Okay, the final example, and again, I'm just following along the text and your theorems. This is called the triangle angle bisector theorem. And this theorem does not involve similar triangles, but there's still a proportional relationship. What the heck does that mean? It means this. Check this out. I've got a triangle. I bisect this angle right down the middle. Now you can see this top triangle here is clearly not similar to the bottom triangle here, because while they have one angle in common, this has no obtuse angle, and this has an obtuse angle, so therefore those triangles are not similar. However, they still have a proportional relationship, and here it is. If I set up the proportion, the end of triangle A over the end of triangle B, and by the end I mean this 8 over 6.5, well then that would go with the side of triangle A, in this case which would be D, over the side of triangle B, which would be 11. The other way to do that would be side over end equals side over end. And that's actually how I set it up over here. I said 8 over D equals 6.5 over 11. And now, once again, I can solve that. You're going to see this on Khan Academy a bunch. And don't be afraid, don't be scared. But one of the things you do know, and keep this in mind, is if one triangle has an 8 and the other has a 6.5, I know that this side has to be bigger than 11 because 8 is longer than 6.5. So D has to be bigger than 11. And so they're going to give you problems where you're like, well, how am I supposed to draw this? Well, which either end is bigger has to also have a longer side. All right, that's all I got. You got some assignment on Canvas to work on to practice this. Again, feel free to use these examples, watch the lecture again, email me if you have any questions, and remember, you can do it.